Hello, folks. We're going to look at this type of problems. This is going to be the fourth. To me, this is the fourth video of chapter 3. But we're looking at projectiles, how they launch horizontally. So whenever we look at some of these problems, we've been drawing vectors to the left, right, and center, but sometimes you just need to draw what's going on. So when something going horizontally, let's draw a table. And here's our Hot Wheel car. Yeah, the table sucks. But here's the Hot Wheel car, and it's traveling this way. There's two forces acting on it. We've got it going motion this way, and there's going to be a force going down. Now, since this against the tabletop, there's no velocity in the y direction. So initially, velocity in the y going down is equal to 0. So all my velocity is in the x direction. It's going this way, according to this picture. Once it leaves, the instant it leaves the table, it's going to have a force going down, gravity. So it's going to go, so you're going to see this force going down, and it's going to have this going across. Now, as it leaves the table, the velocity in the x is going to remain constant. So in the x velocity is constant. Let me rewrite this. X velocity is constant. But the y velocity will increase based on the acceleration of gravity. So in that case, we got acceleration is equal to y final minus y initial, or initial minus y final over time. Y initial is going to be 0. So acceleration is equal to minus y final over time, or acceleration times time is equal to minus y final. Acceleration is minus 9.81. That's the acceleration of gravity times time. Will give me this final velocity. So let's look at the problem. All right. So as you read through this, this is a long problem. All right, we're talking about the high roller, the highest roller coaster in the world. It's in Las Vegas. So we got a bolt that's kicked off the edge of the stratosphere. So the bolt, well, we have initial speed in the x direction, and figure out how far it traveled before hitting the ground. So this is going to end up using a little bit of information. So let's go ahead and go to the next slide. Initial velocity, it's going to be VI, is 0.8, I believe. Yep. And the distance it traveled is 6.76. So we're going to do several things. So what we have, if I draw this building, here's the ground, here's the top of, here's where the bolt was. It had an initial velocity of 6.76 meters in the x direction. It's going this way. There's nothing in the y yet because it's going off in a horizontal direction. It got kicked off. So it got off in a horizontal. So the displacement in x is 6.76. The velocity is 0.8. So if we look at our calculations of distance and acceleration, velocity is equal to the distance over time, or the change in x over the change in time. Know the change in x is 6.76, so velocity is 6.76 meters divided by time. And we know the velocity is 0.8, so 0.8 is equal to 6.76 divided by t. multiply both sides by t, then divide by 0.8. So t is equal to 6.76 divided by 0.8. So 6.76 divided by 0.8. And we're going to have a time of 8.45 seconds. That's the time it traveled 6.76 meters. So how far did it drop? So we want to know what this component is. Granted, it wasn't as more dropping down, but you get the idea. We want to know how far it dropped. So now we're looking for distance with acceleration of gravity. So displacement is equal to initial velocity times time plus acceleration times time squared. Now, we know this acceleration is going to be negative because it's going down. It's all perspective. Our initial velocity is 0, so that goes away. So the distance is equal to a times t squared. X is equal to minus 9.81 times 8.45 squared. So let's go ahead and do the calculation. 8.45 squared, and that's times 9.81. And we're going to get a distance of minus 700 meters. So that's how far it dropped. So so if we reverse our perspective, the building is 700 meters tall. All we're doing is changing the perspective. Instead of looking down as the bulk dropped, we're looking up to see how far it came. Just a difference in perspective. The magnitude is the same number. We're just looking at different directions. That is what I'm looking for to solve these type of problems. Now, based on the equations, the information you give, you may not use this equation, but other distances, go ahead and use the notes from chapter 2 to figure out what equation you need to use. If you have any questions, please see me during Scott time, after school, before school, or during office hours online. Thank you guys.